Thank you for the kind introduction. Hello everyone, we are Team Akatsuki and this is the title of our presentation today. A new model for the vertical structure of the atmospheric pressure and its application to the Venus atmosphere in the supercritical fluid state. We have been working on this theme since last year because we are very interested in the universe. In this presentation, we will tell you about three themes. First, a new model for the vertical structure of the atmospheric pressure. It allows us to know whole vertical structure of the atmospheric pressure of heavenly bodies with a complicated method. Second, a precise analysis of the Venus atmosphere in supercritical fluid state. We have found a surprising result of the Venus atmosphere. We believe that it might be relevant to Venus mysterious phenomena like superrotation. Thirdly, the buoyant force in the air. Why can a balloon fly in the air? We will show you microscopic origin of buoyant and the theoretical explanation of the principle of Archimedes. This is a short summary of our presentation last year. In junior high school, the atmospheric pressure P was explained by the simple idea of the weight of the air pillars and given by equation 1. On the other hand, in high school, we are taught in a different way. The origin of the air pressure is molecular collision. We learned that how the pressure of atmospheric as an open system can be explained by the kinetic theory of gas. A famous equation, the hydrostatic equilibrium. It's based on the idea of air weight, and this pH describes the attitude of dependence of atmospheric pressure. By the way, this is the pressure, air pressure based on the kinetic theory of gas. The number density of a gas molecule per unit volume at the altitude of h is governed by Boltzmann distribution under the potential field of gravity G. From this equation, we derive the same equation of hydrostatic equilibrium. Thus, we have proved the two explanations for the atmospheric pressure, weight of the air pillar and molecular collision are equivalent as far as we treat the atmosphere as an ideal gas. We also derive a new equation for the atmospheric pressure based on real gas by modifying the van der Waals equation. It allows us to treat the atmosphere at a very low temperature on heavenly bodies like the Titan. This year, we have been working further expanding our project. We have visited the statistical thermodynamics and kinetic theory of gas. Now, we introduce our original idea of height proportional density increment approach. This is an innovative model we believe to calculate and simulate the whole vertical structure of the atmospheric pressure very easily. What's HPDI? When we calculate the atmospheric pressure based on the molecular collision theory, we need to know the number density of molecules at each altitude. In our HPDI approach, we divided the H into 100 meters region steps. We can calculate the number density of gas each region with assuming the average molecular constant temperature. We named this approach HPDI. This is our original idea. The HPDI approach includes a gravitational acceleration. Thus, correction for the acceleration is important. Finally, the equation of HPDI is given here. We have also noticed that this equation can be easily modified as shown here. This equation means that we will be able to calculate the whole vertical structure of the atmospheric pressure from a pressure known at any arbitrary point. We have applied HPDI to the atmosphere of the Earth to test its accuracy. This is the Earth's atmosphere. As you know, the ratio of these gases are almost constant up to the altitude of 80 kilometers. The average molecular weight is effective up to the altitude. They perfectly with the results from the state standard atmosphere model. Therefore, we have concluded that our HPDI approach is very reliable. This is the vertical structure of the atmospheric pressure calculated from the pressure at the altitude of 80 kilometers as a reference point. Starting from the very dilute atmosphere about 1 Pascal, HPDI approach perfectly reproduces ground pressure. perfect agreement, the reliability of our HPDR model was proved. It allows us to study the vertical structure of the atmospheric pressure very easily. It will possibly help us investigate the atmosphere of heavenly bodies where we have some difficulties in collecting enough data at many points.
Now, we apply HPDI to the Venus atmosphere. Recently, we got detailed experimental data of Venus atmosphere, which were published by researchers of NASA. The surface temperature of Venus is over 700 Kelvin. We emphasize that value percent of CO2 is 96.5% in the Venus atmosphere. This is phase diagram of CO2. The critical temperature is around 300 Kelvin, while critical pressure is 17 atm. Under conditions of surface of Venus, CO2 behaves as a supercritical fluid. It is very interesting to know which equation fits the state of supercritical fluid CO2 on the Venus. Here is the result of simulation. This is altitude dependence of CO2 dependence Venus atmosphere, as simulated by the equation of real gas. It gives an underestimation of about 10% over the whole range. It probably means that the van der Waals equation under high pressure and temperature needs to be rectified theoretically. This will be an issue of our further study. To our surprise, it's a case of ideal gas. HPDR reproduced the vertical structure of atmospheric pressure very well. These are the results calculated from pressure at ground level. These are results calculated from pressure at altitude 100 kilometers as reference point. It also shows almost the same results from the reference point of the ground level. We have found a puzzling character of the Venus atmosphere. CO2 atmosphere in a supercritical fluid state on the Venus behaves like an ideal gas. What does it happen? Here is explanation. The average kinetic energy of CO2 is estimated to be about 2,200 Kelvin in units of absolute temperature. This value extremely exceeds the estimated to be the stabilization energy of the intermolecular forces, as estimated by Lennard-Johnson potential model. This is the reason. We have found that the supercritical fluid CO2 on the Venus atmosphere is in the ideal gas-like phase within 4 kilometers of the surface. Now, let's go to the third scene. Why can a plane fly in the air? Interpretation of the buoyant force based on the kinetic theory of gas or molecular collision theory. This shows interpretation of the buoyant force based on the kinetic theory of gas. Equation 5 is for the atmospheric pressure in ideal gas. This was derived from the kinetic theory of gas. Equation 16 for the buoyant force is derived from difference in the power a Q-pole receives. On the other hand, it is an interpretation based on the principle of Archimedes. A function of the number density of molecule under the gravitational potential is given here. The buoyant force in the air can be found by the integration. In this way, exactly the same equation can be derived from two different approaches. Thus, we have proved that the buoyant force which works in the air arises from molecular collisions. Now, we come to the conclusion. You can understand why a will fly in the air. The difference in the molecular collision frequency between upper and lower surfaces. Even if a gap is small in altitude, the gradient of number density of gas molecule is caused by gravitational potential. Here is a summary of our presentation. Finally, this study is our original idea and not derived by other researchers. Thank you for your kind attention and listening.
ありがとうございました。それでは質疑応答へと移らせていただきます。ご質問のある方は挙手をお願いいたします。はい、マイクをお願いいたします。
Thank you. Thank you very much for the nice presentation. And I think you have learned very hard to derive the equations. But let me confirm the first equation on the high dependence of the pressure is well-known equation, and I couldn't understand very well about what is new in your model. So could you tell me again about what is new in your model? So you introduced the height dependence of gravitational acceleration, right? G of H. 最初のP エクスポネンシャルで書いてあったあの式は他の例えば圧力の釣り合いとか他のところからもうすでに分かっているさっきおっしゃいましたけど式ですね。で今回新しくモデルとしてオリジナリティというか考えられたポイントというのは、重力加速度の高さ依存性を入れられたところとそれからファンデアワルスの状態方程式を使ったというところでよかったですか？
そうです。
その2つです。はい。わかりました。その2つの効果で随分影響が出るというふうに思っていいですかね。
重力加速度補正を入れたことで、以前は入れなかったら 5% だったんですけど、入れたことで 3% に軽減することができました。
軽減することができました。はい、わかりました。そうですね。非常によく温度とそれから圧力が一致していてモデルで計算された値とですねよく一致していてという話をされたんですけれども、あれはその状態方程式が精度で一致するということではなくて今回のモデルの精度を表していると思っていいでしょうかね。高さのデータはつまりここから非常によく頑張って計算されていいと思うんですが、高さのデータはごめんなさい、温度のデータは他にあったわけですよね。
温度のデータもはいありました。
そこから計算された圧力ということですね。
はいしました。
はい、ありがとうございました。
ありがとうございました。
ありがとうございます。その他ご質問ございますか？大丈夫でしょうか？そうですね。じゃあもう一つ。すみません。お願いします。
日本語で聞きます。今の質問とも関係するんですけど、新しく使っている式は重力加速度 G に高さの補正が入っていることとか、アイデアルガスだけじゃなくてリアルガスもやってみようとかいうことと、これ温度のところね、エクスポネンシャルの中の分母の温度に添え字がついていて、スモール h-50 とかね、さっき150だとか、あれは本当は温度は h の関数ですよね、高さの関数。だけどそれを t50 とか t150 とか th-50 ってこれなんかパラメトライズしてるんですか？つまりそこのところのなんか特別な温度を使うことで、よく合うようになんかしてる
の？その H100 とか入ってるN100 とか入ってるところはその前の値、例えば、100メートルの値の圧力を出したかったらその地上での圧力を入れた上での計算で100メートル出してるんです。
その時温度の値はどこの高さのところの温度を使うんですか？
そのさっきの説明例だったらその0メートルと100メートルの中間値の値の温度を使ってます。
だから
平均の
一番右に書いてあるように0から100の間は T50 っていうのを大体使うとかね、
はい、
そういうふうに使ってるわけね。
そうですそうです。
その区分け方はどうやって決めたの？オレンジと黄色と緑と。
100メートルとか100メートルごとってことですか？50メートルごとでもしていいんですけど、でもそんな100メートルごとと誤差あんま変わらないので、だから昨日100メートルごとにしました。はい、ありがとうございました。
ありがとうございます。ではお時間も参りましたので以上とさせていただきます。大谷中学校高等学校の皆さんでした。ありがとうございました。